Hi, I'm Nithin Varma. I am a postdoctoral researcher at the University of Haifa. This talk is about a recent work on a sensitivity notion for graph algorithms. This is joint work with Yuichi Yoshida of NII Tokyo. Roughly speaking, the sensitivity of any algorithm is a measure of the change in its output as a function of the change in its input. Today, I will talk about a particular definition of sensitivity for graph algorithms. I will first introduce our definition of sensitivity, talk about some important properties of our definition, and then tell you about the connection it has to the study of sublinear and local algorithms. I will then mention our main results and conclude with some open directions. Intuitively, average sensitivity of an algorithm A is the difference between its outputs on two nearby graphs. We think of outputs of algorithms as subsets of edges or vertices. Given a graph G and an algorithm A, we measure the sensitivity of A on G as the difference between outputs of A on G and on a related graph G prime. Here, G prime is a large random subgraph of G on the same set of vertices as G. In particular, the measure of change in output is the cardinality of symmetric difference between A's outputs on G and G prime. Throughout the talk, we denote the cardinality of symmetric difference as the Hamming distance. This is okay because sets are equivalent to their characteristic vectors. Sensitivity is a natural performance notion just like approximation guarantee or running time. Moreover, if an algorithm has low average sensitivity, we can use it to solve problems on large unknown graphs, provided we have access to a large random subgraph of the graph. The situation occurs frequently as it is often hard to obtain full information on large graphs. For example, unupdated or hidden friendships on social networks or link failures in large traffic networks. One can model such edge failures as random edge deletions, and in these cases, using a low sensitivity algorithm, one can get outputs that are close to the outputs on the original graph. Here is a formal definition of average sensitivity of deterministic algorithms. It is the average Hamming distance between the output of A on G and the output of A on G minus E, where the average is taken over the edges E. An algorithm is stable on average or simply stable if it has low average sensitivity. Our definition is easily generalizable as k-average sensitivity to account for multiple edge removals. One feature of our definition is that it is sensitivity averaged over the edges. This is done in order to capture random edge deletions. The second aspect is that we measure the farness or closeness of solutions instead of values. And in particular, we use Hamming distance to measure how far or close two solutions are. There are a few motivations for using Hamming distance. For example, in the case of dynamic graphs such as road networks, a vertex cover corresponds to assigning traffic police persons at intersections. We need to output vertex covers such that it is possible to cover all the roads even in the event of links getting added to the system without moving around the police persons a lot. And Hamming distance captures this kind of cost. Now here is an example of a problem with what we consider low average sensitivity. The problem here is to output the set of all large degree vertices of a graph. Since the removal of an edge can affect only the degrees of its endpoints, the average sensitivity of the given algorithm is big O of 1. However, not all problems have such good stable on average algorithms. Consider the ST shortest path problem. It is a classical problem with a deterministic polytime algorithm solving it exactly. However, the average sensitivity of every deterministic algorithm for the problem is omega n. This fact can be easily argued using the graph given on the slide. We also generalize our definition of average sensitivity to randomized algorithms. In this case, the output of an algorithm is viewed as a distribution over solutions, and so we need to incorporate a distance measure between distributions into our definition. All other aspects of the definition remains the same. We use the earth mover's distance between distributions. Our choice for this specific distance measure is because earth mover's distance can be used to integrate the Hamming distance between solutions supporting the distributions. Here is a quick definition of earth mover's distance. On the right pane, consider two distributions d1 and d2. Assume that they are supported over the same set of solutions, denoted by the symbols S1 through SR. The probabilities in D1 and D2 are denoted using the symbols Pi's and Qi's. We can also consider a complete bipartite graph where the vertex sets on either side are the supports of D1 and D2. Edges are labeled with the cost of transforming the solution at one endpoint to the solution at the other endpoint. In our case, this transformation cost is simply the Hamming distance. Let us define the work needed to move a probability mass of P from a solution Si to a solution Sj to be P times the Hamming distance between Si and Sj. The earth mover's distance is the cost of the optimal way to move all the probability mass from the left side to the right side using the edges in this graph. In a sense, it is the work that we need to do in order to transform the left distribution into the right distribution. As before, we can generalize our definition to the removal of multiple edges also. There are some important related sensitivity notions well studied in theoretical computer science. One is differential privacy, and specifically in the context of edge removals of graphs, edge differential privacy. A key difference is that differential privacy is a worst case notion of sensitivity as opposed to our average case notion. Stability has also been studied in the context of reducing the generalization error of learning algorithms. Next, I will briefly highlight the key properties of our sensitivity definition. We show that sensitivity bounds for removal of multiple edges can be obtained by summing up the bounds for single edge removal sensitivity. Another useful property is that one can compose two algorithms B and C with low average sensitivity to obtain an algorithm A with low average sensitivity. Essentially, the sensitivity of A is the sum of the sensitivities of B and C. This is what the theorem informally says. We use this theorem extensively in our paper to build stable algorithms from component stable subroutines. There is also a corollary of this theorem that is applicable to combine more than two stable on average procedures. Next, I will describe the relationship of the study of average sensitivity to sublinear algorithms and local algorithms. Consider a deterministic algorithm A for some problem, and let's assume that this problem for a graph G is to output maybe some subset of vertices satisfying some property, for example, vertex cover. Consider another algorithm, which we call a solution oracle. The solution oracle gets query access to a graph G, gets an input vertex V, and outputs whether V is part of the solution of A on the graph G. The queries made by O to G are neighbor queries. Let Q denote the average query complexity of the oracle O, averaged over the input vertices V. We prove that in this case, the average sensitivity of A is at most Q. That is, if A has an efficient solution oracle, then its average sensitivity is bounded by the query complexity of that oracle. The same thing can be generalized to randomized algorithms. A randomized algorithm can be viewed as a deterministic algorithm that additionally gets a random string. We generalize this earlier theorem to the case of randomized algorithms and also use this theorem extensively in our paper in order to obtain stable on average procedures. We also study the connection of stable algorithms with local computation algorithms. Consider a randomized local computation algorithm L for a graph problem P. It gets as input a vertex V, tosses random coins pi, and outputs whether V is part of a solution to P on G. L cannot do any pre-processing on G, and the requirement is that its answers on different inputs have to be consistent with a single feasible solution for P on G. We show that if there exists an LCA for a graph problem, then we can come up with a stable on average algorithm for that problem. The sensitivity of our algorithm is at most the query complexity of the LCA. The main takeaway here is that a lower bound on average sensitivity of a graph problem directly becomes a lower bound on the query complexity of LCAs for that problem. Next, I will describe our main results with a focus on our results connected to LCAs. In a nutshell, we design stable approximation algorithms for several important graph problems and also show sensitivity lower bounds. As mentioned earlier, our lower bounds for average sensitivity imply lower bounds on the query complexity of LCAs. Now, one thing to note is that there cannot be sublinear query LCAs for exact versions of maximum matching, global min cut, and min ST cut. Now, additionally, for global min cut, we show that whatever be the approximation ratio, one cannot have a LCA for a purely multiplicative approximation to global min cut with query complexity better than n to the 1 over opt square, where opt is the value of the min cut. The result that I want to focus on, however, is the linear lower bound on the query complexity of LCAs for 2 coloring. With this result, we solve an open problem raised by Shumai, Mansoor, and Vardi on whether there exists sublinear query LCAs for two-coloring a graph. I will conclude the talk with some open directions. Average sensitivity is a new definition, and there are a lot of open questions that need answering. From the perspective of LCAs, the most interesting direction to pursue is to prove lower bounds on average sensitivity. Additionally, research on LCAs can lead to new stable on average algorithms for various problems. It is also interesting to analyze the average sensitivity of existing approximation algorithms. Peng and Yoshida, in a paper published recently at KDD 2020, analyzes the average sensitivity of spectral clustering, and they show that spectral clustering is stable. Other open questions are to design stable on average algorithms for other combinatorial problems, designing stable on average sub-procedures that we can combine using our composition theorems to get stable algorithms, and so on. And there are a lot more other open directions. Average sensitivity is a new area. There are several interesting things to pursue here, and thank you.